Hi children, welcome. A warm welcome to another chemistry class. A warm welcome to a very important chapter in the entire +1 +2 syllabus of chemistry, and it is coordination compounds. So let us have a talk on important questions on complex chemistry, one of the most important chapters from the entire 11th and 12th standard of +2 standards for the competitive examinations. Ready? Yes. First question. That is regarding the Iupac name of complex ion. You know how to name the complex ion. Ligands will be named first. And here the ligand is cyanide. The ligand is cyanide. Cyanide will be named as cyanido, hexacyanido, hexacyanido. That itself is enough to identify the answer. Hexacyanido, only one choice. Now what is the remaining part? Hexacyanido ferrate 3. What is that 3? 3 is the oxidation state of iron. All of you know cyanide is -1. -1 into 6 -6. If this is total -3, this will be +3. So +3 with the -6, you will get -3. And anionic ligands will be named with the metal atom naming 8, ferrate, cobaltate, nickelate, zincate, like that. So it is hexacyanidoferrate 3. 3 stands for the primary valency of central metal atom. That is nothing but oxidation state. Clear? Fine. Next. Hybridization involved in the complex NiCN4 2 minus. NiCN4 2 minus. You see NiCN4 2 minus, nickel undergo what hybridization? A very famous molecule we are learning in the chapter, and you must know the answer also. You may be aware of the answer also. You see nickel is available in what state? Nickel is atomic number 28 and the configuration is 3D8 4S2. In the complex, nickel is +2 state. You see cyanide is -1 with the 4, -4, and this is +2. Then only overall 2 minus. So nickel 2 plus means this electron gone and you are having D8 system. What is D8 configuration? What is D8 configuration? 1, 2, 3, 4, 5, 6, 7, 8. There are 2 unpaired electrons. Right? But all of you know regarding the nature of the cyanide. Cyanide is a strong ligand. Cyanide is a strong ligand. Even though we are not considering that in VB theory, the magnetic properties cannot change. The magnetic nature of nickel tetracyanide is, you must know, it is diamagnetic in nature and you can't have 2 electrons like this. So what assumed is this electron is paired here. So what happens? What happens? This is already paired, this is paired, this is paired, this also will get paired, and one d orbital is free and it undergo 3d, 1 orbital and s orbital and p orbital will take part in hybridization. D, S, P, 2 hybridization as the coordination number is 4. It's a tetra-coordinated molecule. So the hybridization, either it need to be sp3 or dsp2. So being cyanide, when you consider, it is dsp2 hybridization Option 3 is the answer, and hence the molecule can turn diamagnetic in nature. So it is based on the magnetic property we explain this fact. While if we are dealing with the CF theory, we have spectroscopic analysis of the order of strength of the ligand, and all of you know cyanide is a strong field ligand. And it will give you a low spin complex. It is spin paired complex. So the electrons will get paired up. This electron will get paired up and it will go for 1 d orbital free dsp2 hybridization. Clear? And the answer is third choice, dsp2 hybridization. Next, sum of coordination number and oxidation number of metal in the complex. You see En twice, Men twice, En, all of you know it is a didentate ligand, ethylene diamine, that is a didentate ligand. So what is the nature of the complex? What is the nature of the complex? It is M with ethylene diamine, NH2, CH2, CH2, NH2. So it is making a bonding like this, right? Similarly, there are, it's an, you see, there are two En. So second En may be coming like this, second En may be coming like this. You see that? This is second En, ethylene diamine. So one bond, two bond like this, and two bond like this, and there is one C2O4. C2O4 is what? Oxalato. How is the bonding there in oxalato? This is oxalato. This is oxalato. This is oxalato making bonding. You see that? It is basically a octahedral complex. So 2 ethylene diamine makes 4 bond because it is didentate. Ethylene diamine is didentate. So 2 ethylene diamine, 1 ethylene diamine, 2 bond. 2 ethylene diamine, 4 bond. Oxalato is also didentate. So 1 oxalato, 2. Say total of 2 plus 2 plus 2, 6. So coordination number is 6. Coordination number is 6. Now what is the oxidation number? What is the oxidation number? Primary valency. You see, oxalato is -2 charge. This is neutral and this is -2 charge, and chlorine is -1 charge. So M will be +3. This is neutral. This is -2 charge and chlorine is -1. -2, -1, -3 will be compensated by +3. So oxidation number is +3. Oxidation number is +3 and coordination number is 6, a total of 9, and the answer is third choice. This is the correct answer. So sum of primary and secondary valencies. Primary valency, that is oxidation number, easily you can evaluate +3, while coordination number is 6. 9 is the answer. Okay. We want sum of. Next. Number of possible isomers for the complex. Number of possible isomers for the complex. You might have encountered such molecules, and this is a molecule which you can perform. You see that there are 2 chlorine and 2 ethylene diamine. It will give you cis-trans isomerism, out of which trans is optically inactive while cis is optically active. So it is cis, there will be 2 molecules, dextro-levo, and trans only 1 molecule, a total of 3 molecules. The answer will be option first choice. First choice. I will draw the structural details if required. You see that it is cobalt. It is cobalt on the central position. Suppose you are taking chlorine like this and ethylene diamine. This is ethylene diamine which is bidentate ligand. This is a symmetric molecule and this is trans configuration, only one molecule. What about the cis configuration? What about cis configuration? This is cobalt and you have chlorine here and one ethylene diamine like this, one ethylene diamine like this. I am sure you understand this molecule is optically active as it will have chirality. There is a non-superimposable mirror image. There is a non-superimposable mirror image given by this molecule. Isn't it? There is a non-superimposable mirror image given by this molecule. And if you want to know, I will draw the non-superimposable mirror image also, which will come like this. You see that? There is cobalt 1, 2, 3, 4 and 2 chlorine coming like this and one ethylene diamine, another ethylene diamine like that. You can see the two molecules are non-superimposable mirror images to each other. While that is not possible here. That is not possible here. You see this molecule? You see this molecule, if you try to place over here, it makes a non-superimposable mirror image. And hence, they are optically active, they are chiral. If one is dextro, other is levo. So, a total number of isomers given by this molecule is 3. Cis, dextro, levo and trans. So, it is cis, dextro and cis, levo. If this is dextro, this will be levo or vice versa. And trans is only one molecule, a total of 3 isomers. An NCERT example only. Okay, next. The correct increasing order of trans effect of the following species. Trans effect, that is out of syllabus question, but once appeared in the examination. Trans effect. Trans effect means an existing group goes and a new group comes. Imagine, in a complex, a group is replaced. A ligand is replaced. What will be the position of the new ligand? Suppose 2 new ligands are coming. Will it occupy cis position or trans position? That is decided or that is formulated as trans effect. It is based on the trans effect. What is the order of trans effect? This you can note down as an order of trans effect, trans kinetic effect. You see, fluoride, water, OH, etc. having low trans effect, while ammonia having bit high, pyridine having again high, chlorine, bromine, iodine bigger, thiocyanate, nitro, it goes like that. H, higher trans effect, NO, CO, Cn minus, they are having higher trans effect. This probably is an experimental order of trans effect. Greater the trans effect, greater the tendency to come at trans position. Suppose 2 new chlorine coming. Suppose ammonia replaced by chlorine. Imagine ammonia replaced by chlorine. Ammonia replaced by chlorine. 2 ammonia replaced by chlorine. The 2 new chlorine will occupy trans position. Suppose chlorine is replaced by ammonia. The 2 new ammonia will come at cis position because trans effect of chlorine is greater than ammonia. So the one which having greater trans effect will come at a trans position. That is what the observation. So the trans effect, which one we can take? The order is available. Maximum trans effect is cyanide, then comes phenyl, then comes bromide, then comes ammonia. You see, cyanide, phenyl, bromide, ammonia. So suppose you are replacing bromine with ammonia. The new ammonia will come at, suppose 2 bromine replaced by ammonia in a complex. Just imagine, you have a square planar complex. Imagine 2 bromine you are replacing with ammonia. The 2 ammonia will come at a cis position. Imagine in a complex 2 ammonia replaced by 2 bromine. The new 2 bromine will come at a trans position. This is what called a trans effect. Okay. Next. Jahn-Teller effect is not observed in high spin complexes of. You see, Jahn-Teller effect means molecular distortion. Molecular distortion. Molecular distortion due to unsymmetric electron distribution. Unsymmetric electron distribution. You see, if you are taking D4, high spin complex D4, all of you know this is T2G, this is T2G orbital, and this is EG orbital. T2G and EG orbital. Okay. Suppose I am taking D4 complex, which is high spin, means maximum number of unpaired electron. How is the configuration going to be? How is the configuration going to be? Simple, no? 1, 2, 3, 4. Hope you understand. This is an unsymmetric distribution of electrons. In T2G, it is symmetric. Here it is symmetric. Here it is unsymmetric. So there will be molecular distortion. This is called the Jahn-Teller effect. Our question is, which is not observed. Suppose you are taking D9 system. Imagine you are taking D9 system. What will happen? This is T2G orbital and this is EG orbital. D9 is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. Once again, you can find it is unsymmetric electron distribution. Here it is symmetric, here it is unsymmetric. So there will be molecular distortion. Hope you understand. Now option C, D7 system. What is going to be D7 system? D7 system. This is D7. 1, 2, 3, 4, 5, 6, 7. You can see here it is symmetric, here it is unsymmetric. You see one, it is singly occupied. It is unsymmetric electron distribution. Again, there is molecular distortion. What about D8? That will be the answer. Because all other are having Jahn-Teller effect. All other having Jahn-Teller effect, answer should be option D. I mean fourth choice. D8 system. 1, 2, 3, 4, 5, 6, 7, 8. Now you see it is symmetric. Here all occupied, here it is singly occupied. It is a symmetric electron distribution. So here the electron distribution is unsymmetric. Here the electron distribution is unsymmetric. Here the electron distribution is unsymmetric. While here the electron distribution is symmetric. And there is no Jahn-Teller effect. And the answer is option fourth choice. I think it is clear. So unsymmetric distribution of electron density across the T2G EG orbital create a molecular distortion called the Jahn-Teller effect. Okay. Next. Jahn-Teller effect, sometimes also known as Jahn-Teller distortion, describes the geometrical distortion of molecules or ions that is associated with a certain electronic configuration. What is certain electronic configuration? Unsymmetric electronic configuration. Already we have seen. Next question. Correct increasing order of wavelength of absorption in the visible region for the complex CO3 plus. See, correct increasing order of wavelength. Wavelength maximum means frequency minimum. Wavelength maximum means frequency minimum. Frequency minimum means T2G EG splitting is minimum. T2G EG splitting minimum means weak ligand. So for a weak ligand, the splitting will be minimum, frequency will be minimum, wavelength will be maximum. So the answer is first choice. First choice. You see, water is a weak ligand. The next is ammonia and En is a strong ligand. So water is a weak ligand. So the splitting will be minimum. So the energy for transition will be minimum. Frequency will be minimum. Wavelength will be maximum when it is water. Then comes ammonia and then comes En. Clear? Clear? Yeah. We want increasing order of wavelength. So wavelength is maximum here and wavelength is minimum here. Suppose instead of wavelength it is frequency asked, just opposite. Just opposite. So stronger the ligand, stronger will be the splitting, greater will be the energy for transition, greater will be the frequency for transition, lower will be the wavelength for transition. Okay, next question. Correct order of stoichiometries of AgCl formed when AgNO3 in excess treated with complexes COCl3 6 ammonia, COCl3 6 ammonia. It will be like this. It will be like this. COCl3 6 ammonia will be CO ammonia 6 times Cl3. There are 3 chlorine outside. You will get 3 AgCl precipitated. The number of chlorine available outside, that means ionizable chlorine. These are 3 ionizable chlorine. So you will get 3 mole AgCl when treated with excess silver nitrate. You will get 3 mole AgCl. Second one, 5 ammonia, 3 chlorine. So it is going to be CONH3 5 times. Now what happens? 1 chlorine will come inside, 2 chlorine will be outside. Werner's experiment. 2 chlorine ionizable and therefore you will be getting 2 mole AgCl precipitated. What about the third one? It is CONH3 4 times. Now 2 chlorine will come inside. There will be only 1 ionizable chlorine. You will be getting only 1 mole AgCl precipitate. So it is 3, 2, 1 respectively. Answer is option 3. Answer is option 3. Werner's experiment. One of the most important topic from that chapter in the initial portion of the chapter. Okay. Why? Because the coordination number has to be fixed. Coordination number has to be fixed. 6 here. Sorry. Here also 5 plus 1, 6. 4 plus 2, 6. So secondary valency of metal found to be fixed. That's what happened. Next. Example of sigma bonded organometallic compound is, see, metallocenes are pi complex. Metallocenes are pi complex and the answer is Grignard reagent. Answer is Grignard reagent RMGX. This is a sigma bonded complex between carbon and magnesium. The others are pi complexes and these are the molecules. Ferrocene, the aromatic pentagonal ring sandwiching iron, ferrocene, cobaltocene, ruthenocene. Okay, they are pi complexes, that is sandwich type molecules. Next, correct statement with respect to MnCN6 3 minus. MnCN6 3 minus. See, manganese D5S2 configuration. Manganese is D5S2 configuration. And we are talking about manganese 3 plus. We are talking about manganese 3 plus, so it will be D4 configuration. This is D4 configuration. 1, 2, 3, 4. So what will happen? Octahedral complex. Octahedral complex can be two type. Either sp3D2 or D2sp3. Here what it is going to be? Simple, no? Cyanide. Cyanide being a strong ligand, what happens? It is D2sp3. So what is happening? One of the electron will be shifted to here, so that the electronic configuration is going to be, this is a paired electron system, and the two electron will be like this. These two orbital will be utilized for hybridization. D2sp3 hybridization. These two d orbital, outer s orbital and p orbital will be utilized. So what is the situation? It is octahedral, no doubt. Octahedral. Octahedral, third choice. D2sp3 hybridization. It is D2sp3 octahedral. D2sp3 octahedral, third choice. Next, geometry and magnetic behavior of the complexes. Geometry and magnetic behavior of the complexes. See, this is a very famous molecule. Nickel tetracarbonyl tetrahedral sp3 hybridization. sp3 hybridization, and it is diamagnetic. It is diamagnetic. It is tetrahedral geometry and diamagnetic. Second choice is correct. Tetrahedral geometry and diamagnetic. Second choice is correct. How is going to be tetrahedral? How is going to be tetrahedral? All of you know nickel tetracarbonyl. Nickel is 0 oxidation state. Nickel is 3D8, 4S2, and tetracarbonyl, it is 0 oxidation state. What is going to be D8? 1, 2, 3, 4, 5, 6, 7, 8. This is D8. And there are, yes, 2 electrons. So one of this electron will be migrating here, and one of this electron will be migrating here, and this s orbital is made free. And there are p orbitals. So 4s orbital and 4p orbital will undergo hybridization. It is sp3 hybridization, and hence it is tetrahedral, and all electrons are paired up. These two electrons will get paired up, and it is diamagnetic in nature. Okay, so sp3 tetrahedral diamagnetic. Next question. Correct electronic configuration for this. Correct electronic configuration. Simple investigation will tell you iron 2 plus state. K4FeCN6, iron in the plus 2 state. What is the character of iron? Iron is D6S2. Therefore, iron 2 plus will be D6. And see the nature of the ligand. Ligand is a strong ligand. Ligand is a strong ligand. So what is the configuration? What is the configuration? You see T2G orbital and EG orbital will maintain large energy difference. They will maintain large energy difference from the barrier. And we have 6 electrons. 6 electron will be, how it is placed? 1, 2, 3. Fourth electron want to go there but unable to. So it will be paired here. 4, 5, 6. This is T2G orbital and this is EG orbital. So the configuration is T2G 6 and EG 0. T2G6 and EG0. Answer is first choice. And there can be question calculating CFSE. There can be question calculating CFSE. What is the crystal field stabilization energy for this complex? What is CFSE for this complex? CFSE means crystal field stabilization energy. I am sure all of you know this is dropped by minus 2 by 5 delta O, while this is increased by plus 3 by 5 delta O. How to calculate CFSE? It is minus 2 by 5 into number of electrons here. It is 6 plus 3 by 5 into number of electrons here. It is 0. That of overall delta O plus the forced pairing happening. There are 3 forced pair electron, so it is 3p. P means pairing energy. P means pairing energy. So how is the calculation coming? Minus 12 by 5 delta O. This is cancelled. Plus 3p. That is the answer. So there can be question calculating CFSE. Please work out that also. How to calculate CFSE? The dropping energy into number of electron here, increase in energy into number of electron here, and if there is forced pairing, that has to be added. As many pairing, as many P. Here there are 3 forced pairing, so it is 3p. I think it is clear. Next. Anyway, here the answer is just the configuration T2G6 EG0. T2G6 EG0. Next. Increasing field strength. Increasing field strength. That is described in the NCERT textbook. A long order is given. Please learn that. A sure short question. And the answer is 4th choice. Answer is 4th choice. Cyanide, oxalato, fluoride, thiocyanate. And this is the complete order. Next. Among these isomers are, you see chlorine trans, this is trans. Chlorine trans, this is trans. These two are identical. Chlorine cis, this is cis. Chlorine opposite, this is trans. So molecule 1, 2, 4 are same. Molecule 1, 2, 4 are same. And third one is isomer. So suppose you are finding a combination 1 with 3 with anybody. 3 versus anybody. 3 versus 1 or 2 or 4. It can be 3 versus 1, 2, 4. They will be isomers. 3, 1 is isomer. 3, 2 is isomer. 3, 4 is isomer. And it is cis-trans isomerism. Okay. Next question. 15th one. The two structures given are. They are same. This is cis and this is also cis. Both are cis. Same molecule. Next. This is the special type of isomerism. All of you know. Facmer isomerism. You see, chlorine occupy the face. The 3 chlorine occupy the lateral face of the octahedron. That is facial isomerism. Facial meridional isomerism. You see ammonia in the meridional plane. You see the 3 ammonia in the meridional plane, while here ammonia in the face. Here 3 ammonia in the face, lateral face of the tetrahedron. So this is facial isomerism. while this is meridional isomerism, the famous called Fakmer isomerism. So three ligands coming across over a lateral face, on the corner of a lateral face, facial isomerism, coming in a plane, meridional plane isomerism. And it's a part of geometrical isomerism, a special type of geometrical isomerism performed by the molecule Ma3B3. Ma3B3. Facial meridional isomerism. And I will draw that structure and show you. You know that if you take an octahedral complex M, imagine if it is coming like this. Say A. It's coming across the lateral face. That is facial isomerism. While what is meridional? What is meridional? You take the plane M 1, 2, 3, 4, 5, 6. Suppose it is coming like this over the meridional plane. Over the meridional plane. That is meridional isomerism. This is facial isomerism. And this is meridional isomerism. Fakmer isomerism, a type of geometric isomerism. Okay, shown by the molecules Ma3B3. At least A3 is required. Next, how many stereoisomers are possible for the complex given? That is MABCD type. You look at the molecule. Isn't it like this? MABCD type. It will show three configurations. What are the three? You see, M is platinum. A, B, C, D type. M, A, B, C, D type. You will have three configuration. A, B, one configuration. A, C, next configuration. A, D, third configuration. So you fix the position of A and make a change in the relative position of the A. Like AB, AC, AD, you will get three configurations. And think about how many configurations you get in a octahedral complex M, A, B, C, D, E, F. Think about that. This is square planar complex. Platinum makes square planar complex. M, A, B, C, D. Three configuration. A, B, A, C, A, D. What about octahedral? M, A, B, C, D, E, F. Work out. Find out. Next. Yeah, this is what the trans effect question. This is what the trans effect question earlier I told you. You see here what happens. Chlorine replaced by ammonia. There are 4 chlorine. Out of 4 chlorine, 2 chlorine remain. 2 chlorine replaced by ammonia. So when chlorine replaced by ammonia, hope you remember what is the order of trans effect. Ammonia has lower trans effect than chlorine. Try to remember what the order earlier we have seen. So when chlorine replaced by ammonia, ammonia will come at a cis position. This is trans and this is the answer. So you will get Q. Answer is option B. Once again, this is the trans effect. You see, ammonia replaced, chlorine replaced by ammonia. This is replaced by ammonia. Ammonia has a lower trans effect. Ammonia has got a lower trans effect. So what happens when chlorine replaced by ammonia? Ammonia will come at cis position. Wow, this is another question. Aqueous NaCl added to this. You see, there were 4 ammonia. Out of 4 ammonia, 2 remain and 2 new chlorine comes. So here, ammonia replaced by chlorine. what will happen? Chlorine has got a greater trans effect. So chlorine will come at transposition. Chlorine will come at transposition. Answer is option B. Chlorine will come at transposition. That is the application of trans effect. It is used for producing pure isomers. Particularly important in medicinal chemistry, where we want pure one isomer. Next. Stability constant. Stability constant means equilibrium constant for this reaction. Option B. Equilibrium constant for that given reaction is called a stability constant. And the reverse is instability constant, dissociation constant. And we represent that in terms of the form beta n. N stands number of ligand, coordination. Suppose 4 coordination, we call it as beta 4. 6 coordination, we call it as beta 6. Stability constant. The given complex is more stable than. You see, there is En available. Here there is no En. So definitely this is more stable than B and C. What about A? Of course it is more stable than A also. Answer is D. See, in the given complex there is ethylene diamine. Ethylene diamine having a chelating character. It is having a macrocyclic stability effect. It makes a didentate character chelating character. So it forms a ring type complex increasing the stability, which is not available here and here. So the given molecule is stable than B and C, no doubt. Then what about A? What about A? There is En2, there is En2, there is chlorine, but here cobalt is 3 plus, here cobalt is 2 plus. You see that there is a positive charge. This is neutral. So in the option A, cobalt is plus 2 state. The compound given in the question, cobalt is plus 3 state. Greater the oxidation number, greater the stability. Okay. So the given molecule is stable than all the given. Next. Which can show geometrical isomerism. Which can show geometrical isomerism. This can show geometrical isomerism. PT glycinato 2. How is able to perform geometrical isomerism? How is able to perform geometrical isomerism? 1, 2, 3, 4. 1, 2, 3, 4. You see that? COO minus. Imagine here comes COO minus CH2 NH2. COO minus CH2 NH2. I think you understand this is cis. If you make it opposite, that is trans. COO minus CH2 NH2 NH2 CH2 COO minus. This is trans. So cis trans isomerism possible for option A, while that is not possible here because it is symmetric bidentate ligand. A symmetric bidentate ligand cannot give you such a configuration. So in B there is not. In C it is possible. Cis and trans, very famous molecule, I don't have to explain. You see, platinum square planar complex, 2 ammonia, 2 chlorine, cis and trans configuration, you know that. And the answer is option D, both A and C. Both A and C. Clear? Next question. The primary valence and secondary valence. Primary valence and secondary valence. Primary valence means oxidation number. This is neutral, sulfate 2 minus, so this is 2 plus, primary valence is 2 plus, so the answer is option D. Because primary valence 2, only one choice. What about secondary valence? 5 ammonia and 1 water molecule. Secondary valence is 6, it is 2 and 6. Simple question. Next. Expected Van der factor for the dilute solution of complex. A dilute solution means we are expecting degree of dissociation 100%. When the degree of dissociation is 100%, alpha is equal to 100%, I factor is equal to n. See, when the degree of dissociation is 100%, Van der factor is equal to n. N means number of particles obtained by ionization. This, when ionizes, you get a complex and 3Cl minus. This is 1,3 type electrolyte. One cation, 3 anion, a total of 4 particles. N equal to 4, I equal to 4. Option D. So the number of particles is 3 chloride and 1 cation. 1 complex cation and 3 chloride, total 4 particles, N is equal to 4, and when alpha is 100%, I factor is equal to N factor. Okay, next. Ligands arranged in the order of increasing field strength. That's a repetition question. According to the spectrochemical series, what is the order? You have to learn. Anyway, 2 choices you can eliminate, B and C, because I am sure all of you remember carbon monoxide is maximum and the correct order is option D. Bromine, iodine, chlorine, sulfide, fluorine, OH, cyanide, CO. Right? So option D is the correct answer. So you have to by heart that order. Spectrochemical series, very important. Okay, next. Iupac name of Na2FeCN5NO. Na2FeCN5NO. Sodium pentacyanide. Sodium pentacyanide or cyano, no problem. Cyanide is the new terminology, cyano is the old terminology. So sodium pentacyanide. Nitrosyl, option D is correct. Sodium pentacyanide, nitrosyl ferrate 2. How it is ferrate 2? Here it is 2 positive charge. Here it is 5 negative charge. So 5 with plus 2, 3, and this is also positive charge in the complex. This is positive. So it is 5 minus 5. Here it is plus 2 plus 3. So this will be plus 2 state. Iron will be in the plus 2 state. Iron will be in the plus 2 state. Nitrosyl is a neutral ligand. But in the complex, it will transfer 1 electron to iron. And that is the reason for color observed in such molecules. Charge transfer, ligand metal charge transfer. Reason for color. Okay, so here nitrosyl is plus 1, cyanide is minus 1, minus 1 into 5, minus 5, minus 5 with the plus 1, it is plus 4, and there are 2 sodium. Obviously, iron will be plus 2 state. Okay, right. So the answer is option D. Iupac name of the molecule. Iupac name of the molecule. Chlorido, 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 chlorido. Bis-ethane 1,2-diamine. Chlorido, bis-ethane 1,2-diamine. Nitrito-N. Nitrito-N. Second choice is correct. Chloridobis, ethane 1,2-diamine, nitrito-N, cobalt 3 bromide. What is this nitrito-N? Nitrito-O. See, if it is written NO2, it is nitrogen getting connected. Nitrito-N. Suppose it is written ONO, oxygen getting connected, then it is written nitrito-O. So ambidendate ligand, you will be calling like this. This you will be calling as nitrito-N. Suppose it is written like this, nitrito-O. Clear? That's it. Option B. Next one. 100 ml 0.1 molar solution complex with the formula given Curdy white precipitate mass 1.43 gram. The complex having the formula is. See, what is that Curdy precipitate obtained? It is nothing but AgCl. So how much AgCl you get? How much AgCl you are getting? AgCl you are getting 1.43 gram AgCl. That means 1.43 divided by 143.01 mole white precipitate AgCl you are getting from 100 ml 0.1 molar solution. 100 ml 0.1 molar means molarity into volume in liter, 0.1 into 0.1, 0.01 mole. So 0.01 mole of complex. Once again, the experiment conducted. See I told you earlier, Werner's experiment, famous Werner's experiment. He was able to explain first ever coordination theory based on fundamental experiments he has conducted on this kind of calculations. And of course, the conductometric techniques. You see that? 0.01 mole of the complex, you are getting 0.01 mole AgCl. That means 1 mole complex will give you 1 mole AgCl. That means 1 chlorine is outside. There is 1 chlorine outside the coordination sphere. Then only this can happen. So what is the formula? 1 chlorine outside the coordination sphere. What is the formula? Option B. Here there are 2 chlorine outside. Here there is no chlorine outside. And this we can't accept. We want a particular systematic formula. So the answer is second choice, option B. Next question. Bridge bonds are present in. Cecil salt is, it is a pike complex. Cecil salt, it is pike complex. This is what the molecule is. PT, Cl, and it is making a pi bonded complex with ethene. This is what the molecule is. Then ferrocene, few minutes back I have shown the structure of ferrocene. Metallocene, ferrocene, cobaltocene, ruthenocene. There are no bridging bonds. What about Mn2CO 10 times? This is Mn2CO 10 times Mn. This is how Mn2CO 10 times. In some of the configuration, it can have a bridging bond, but usually not. Some of the configurations, they carry different configurations. There can be. But the most important example commented in the textbook, I am sure all of you know, it is the last one, and that is the answer. This is the answer, option D. Option D is the answer, where you might have seen in the textbook, the bridging bonds are given like this. Even remember, there are molecules of the same molecule with the different configurations without bridging bond. But this is one example if we strictly adhere to NCERT and there are no combinations given. We can say this is one example quoted in the textbook with a definite case of bridging bond, and the answer is option D. Option D. There is a bridging bond, and this is what called a bridging bond. Bridging means connecting between the two metal centers. Okay. Next. Oh, structure was given here. Yes, fine. You see, this is bridging bond. This is what? Bridging bond. Next. The geometrical shapes of NiCl for 2 minus and NiCn for 2 minus. NiCn for 2 minus already we have seen. It is square planar. DsP2 hybridization, square planar. What about NiCl for 2 minus? It is sp3. All of you know. It is sp3. So the answer is option B, sp3, dsp2. If you want, we can just examine what is NiCl for 2 minus. It is nickel 2 plus system, and it will go for D8 configuration. It is D8 configuration. This is D8 configuration. But you see that chlorine is a weak ligand, no? And the complex is having a dimagnetic moment. Complex is having a magnetic moment close to 3. Some 2.7, 2.8. That means there are two unpaired electrons. So this electron has to be like this. Therefore, it will go for the hybridization, sp3 hybridization. sp3 hybridization tetrahedral. So it is sp3 tetrahedral. Other one is dsp2 square planar. Right? So these are some most important questions from the most important chapter, I would say. One of the most important chapter, coordination chemistry. Right? Learn the chapter well and go through as many questions as possible. Right? We will meet with another class, another chapter. Until then, bye. See you. Take care.